I don't think so. Lubrication. Ignition. No, I don't think so. Torque monitoring.
See anything in there in your engine fuel control?
No, sir. Looks like we went from like thrust reversers, afterburners into bearings and seals, and then into gear reduction and
Okay.
yeah.
Let's go. Hey, let's go.
Where's my refill, man?
Yeah, they were out. I put in a request form for you though.
Always. There we go.
All right. So let's go into engine fuel and control.
Oh, gosh.
So I put the ATA chapter, excuse me, up there occasionally. ATA chapter, do you guys talk about this in general? ATA, Air Transport Association?
I don't think so.
Okay, so ATA is an organization of air transport carriers, and what they do is they set how manuals are laid out. So engine power plants is like 72, is chapter 72. When you get into fuel and control, it goes to 73. So let's say you wanted to do something with a fuel nozzle, you go to fuel and control. It just makes it a little bit easier to find your way through things on the maintenance manual. The smaller aircraft, not so much the business jets anymore. The business jets all use ATA chapters also. They use them all the way from the wheels and brakes all the way up to the trim and electrical systems. So know that you'll find an ATA chapter for if you're looking for parts or you're looking for maintenance. You go to those specific chapters. And you kind of get onto it after a while. You would remember it. So let's say you needed a gasket or an O-ring for a fuel nozzle when you install it. That's where you find it, right there. If you go look at the parts catalog, it's going to be under 73. Now, a lot of times, these parts manuals, they may not list or show you a picture of maybe like an O-ring, but it'll tell you about the assembly. So it'll tell you that you have a gasket, you have an O-ring, you have a nozzle, and it'll list all the individual parts, but you may not have necessarily a photograph or a line drawing of that part. So know that sometimes it's not real helpful, but most of the time, 99% of the time, if you need something, go right to that chapter. It's going to be in the parts catalog or it's going to be in the maintenance manual. So one translates into the other. Okay, so turbine fuel. Okay. So the fuel system, its primary purpose is to deliver fuel to the burner section. So we've already got compressed air there. We're adding fuel, which is going to add thermal energy. And this system has to deliver the fuel schedule. So the engineering people who build the engines, determine what the schedule is for the fuel, depending on a couple of different things, and I'll show you what those are down the road there a little bit. But this is all the different operating parameters of the engine. It also has to deliver the fuel in a very fine mist into the combustion section. Now we can deliver it as a mist into the combustion section. Remember also the combustion section could be pretty darn hot. And so when this fuel enters the combustion section, it'll start as a droplet, but it'll turn into a vapor very, very quickly because of the conductive heat inside the combustion chamber. Okay, so jet fuel is higher viscosity. Jet fuel is easier to handle, easier to maintain and control because it is a little bit thicker, a little bit heavier, it is less flammable. It ignites at a lower temperature, but you really start getting the heat out of it once you start compressing it. Turbine engines run on gasoline, would you guess?
Sure, they can.
Yeah, they can, sure. A lot of times there's a little adjustment you have to make. Sometimes the FADEC, if you're running a FADEC, it will also sense the weight of the fuel and the density of the fuel and will compensate compensate because of the different volatility of the fuels. Gasoline's going to burn a little bit hotter, a little bit leaner, so you're not going to be creating as much thrust pound per pound of fuel, but certainly it can run on gasoline.
What did you call that when this ignites without
And what?
when it ignites without you wanting to ignite it?
For pre-ignition or detonation?
Detonation. That was it.
Yeah, you have detonation in a reciprocating engine. You wouldn't have it so much in a turbine engine because the pressures are always going to be pretty even and the fuel is going to be metered according to the air pressure that moves into the combustion chamber. So as long as fuel is being added, you have the temperature from the compression of the air, but you also have the temperature that's coming back off of the containment that is the combustion chamber. So that temperature is going to cause it just to continue to burn. Okay, so the fuel control is the only way to control the power output on a turbine engine. We're going to control the flow of fuel into the combustion section. Reciprocating engines, the other way around, we're going to more control the airflow, and that's going to create a proportional amount of fuel to the airflow. In the case of a turbine engine, we can increase the airflow simply by adding more fuel to it and causing it to draw more air, more air into it. Now, because of the mass in turbine engines, you've got those big wheels spinning inside there. They're slow to respond to changes in power and output, power and RPM. Those big wheels have to accelerate the air inside the engine. They're taking advantage of the heat that's created, pushing it across turbine wheels, and those turbine wheels then are turning the compressor. So all of this has to be spooled up or allowed to spool down, and it just takes a little bit of time to do this. It's not like a reciprocating engine where it's almost instantaneous. It's called time to excel, or time to decel. So if you run an engine in a test cell, one of the things that you'll be looking for is time to excel from a throttle position or time to decel from a throttle position. And what this is going to tell you is the performance of the engine. Generally, engines that are built with better compression ratios will take a little bit longer to accelerate because they're having to move that extra air. Okay, so the fuel control has to be able to meter the correct amount of fuel to accelerate, decelerate, maintain RPM and power, without overfueling. So if we overfuel the engine, what happens? What are we talking about here? Get too hot. Yeah, get too hot. Why would it get too hot?
Rest.
What about the air to fuel ratio? What happens to the air to fuel ratio when you overfuel?
Rich.
You go too rich. Exactly right. Too rich. So that can overstall, overtemp the engine. If you're trying to start the engine, it can stall the engine. So the fuel control really has to meter the fuel very carefully, depending on quite a number of different things. That's the air mass of the engine that enters the engine, the throttle lever angle, anymore, and quite a number of other things, temperatures in the compressor and so forth. So overfueling is a very, very bad thing. So I'm sitting in a jump seat on a 727, American 727 several years ago in Chicago. And there's a whole line of airplanes ahead of us. There was another American, there was a United, there was a Frontier, there was all these different guys. And typically when it's a long taxi and a long wait, they'll just run on one, maybe two engines if it's a 3-engine airplane, just to save fuel. You can save a significant amount of fuel if you're in line for 20 or 30 minutes. And so what happens is you're sitting there in this line, one guy blowing his exhaust into your face, and then the next guy blowing the exhaust into the next guy's face, and so on and so forth. So there's a lot of air movement between the aircraft. And so I think the guy in front of us was American. We were American. And of course there's this like rivalry amongst all of the airlines, right? So these other guys are all jackasses. They don't know how to fly an airplane, right? Because we know how to fly the airplane. We're really smart to do it. So we're sitting there, and this guy is a 737 twin engine airplane right in front of us, lights the other engine, starts it. This fireball comes out of this thing about 12 feet long, and it just persists. Just keeps coming out, just keeps coming out. Well, what happened is they overfueled the engine. So the older style engine had a mechanical fuel control on it, and it was possible to overfuel this engine. When they did so, now they've overtempt this thing. All this fire coming out the back of this is overtempt the turbine. So this guy now, of course, everybody saw it. Everybody's on the radio. They're all talking shit about this guy. And so, but he knows what he's got to do now because their engine recorders said that he's overtempt this engine. He had to turn out a line and go back to the gate because now he's got an overtemp inspection that has to be completed on the engine. So don't you just know those people were not real happy about that. So this kind of stuff happens from time to time, not real often, but it does happen from time to time. But overfueling an engine is going to cost you an inspection because they have to go into the borescope and make sure that you didn't melt something inside the engine. So that's, and of course I thought it was funny that hell, we moved up in position instantly. Okay, so underfueling is just going to slow down the engine. It won't pick up any speed if it doesn't have enough fuel. It's just a weak mixture or a very lean mixture. So if you end up with a case of a hung start is just a case where an engine won't accelerate, doesn't want to accelerate. And by grabbing the throttle, that's not going to help it. Because then you're not moving enough air through the engine. Not moving enough air through the engine, you add extra fuel to it, now you've gone rich again, and now you're overfueling. So you've gone from one extreme to the other. Now this isn't so possible with FADEC controlled engines anymore. Most every modern engine is FADEC controlled, but there's still quite a lot of mechanical controlled fuel controls out there. They're like a carburetor. Some of you have seen your neighbors go out to work in the morning, and they get out there, and Harley's a good one, a good example. I got a neighbor that has a Harley. So you'd think a Harley would idle. Harleys don't idle. They have to always go vroom, 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 right? But only like at 6 o'clock in the morning. That's a good case of mechanical fuel control, in which case the owner is trying to warm this thing up. It'll warm up just as fast by driving it, just some simple miles an hour, not gunning the thing. And the engine will probably live a lot longer instead of dumping a lot of fuel into the cylinders, washing the oil off. Okay, so you've got three basic kinds of fuel controls. And I'm just going to touch lightly on the FADEC stuff and real light, even lighter on this other stuff. The mechanical fuel controls. Now this is all cable controlled or push rod controlled fuel controls. It's direct mechanical attached to a throttle. Could be a helicopter, could be an aircraft, a fixed wing aircraft. Doesn't matter so much. It's a mechanical fuel control. Most of the old mechanics call them carburetors anymore, because they operate pretty much like carburetors. And in fact, they work a lot. All three of these actually work a lot like governors on propeller systems. Okay, propeller governors. They use flyweights in them to very accurately measure the RPM that they're being fed. Okay. So mechanical fuel controls, still a ton of them out there. If you ever have to change a fuel control with a mechanical, and you're dealing with a mechanical fuel control, you're going to end up doing what they call an engine trim. An engine trim has to be done. It's within certain parameters, and every aircraft maintenance manual has certain parameters. Temperature, wind conditions, and humidity has to be set up within those limits so that the engine produces its power. Another thing, if you ever do a trim, you have to do it with the aircraft pointed into the wind. Write that down. Everybody write that down. The FAA came in here about a year ago and said, nobody knows how to do a trim. I said, well, nobody does those things anymore. And the reason they knew that was because there was a question on the written exams, and almost every one of our people missed that question. You have to have some consistency when you do the engine trims. And one of the consistent things is that the airplane has to be pointed into the wind. You can't have the wind blowing up the tailpipe. You can't have it quartering across the aircraft. It has to be blowing onto the nose of the airplane. Okay, the second type of fuel control is the electromechanical. And it's only one step up from the mechanical. It's still pretty simple. It uses relays and electrical valves to open up metering holes within the fuel control. So when certain prescribed conditions are met with the fuel control, what basically happens is, as you push the throttle forward, it raises the fuel pressure. More fuel flows through the fuel control at that point. Valves begin to open one after another in sequence to allow more and more fuel in steps to move through the fuel control. Now this is a lot more accurate than the mechanical fuel control, but now we move on to the electronic FADEC control. Gets rid of all those problems. So you have to trim an engine after you change the fuel control with a FADEC? No. All you do is a leak check. All you do is a leak check. And that's just to make sure that anything that you put on seal-wise isn't going to leak and you're not going to have a fire on your hands. Because the FADEC will self-trim the system on the engine. It's taking a lot of sensing information off of the aircraft and is feeding it all into the computer. Okay, so the fuel system is going to have a lot of strainers and screens. This is stuff that, as maintainers, you're going to get involved in. You're always going to be changing filters, always going to be inspecting filters. What kind of stuff would you find in a filter?
Dirt.
What?
Dirt.
Dirt? Yeah, a little bit dirt. Fuelers get dirt in the system. What else?
Hopefully not metal parts.
Yeah, complete metal parts.
Rubber.
Yeah, pieces of seals. Seals get cut. Seals deteriorate. I have to tell you that when you put a seal in turbine fuel, it better be the correct compound. So a seal is not a seal is not a seal. Use the correct correct compound, what will happen is turbine fuel will cause the synthetic neoprene seal to swell. And once it's captive, it's fine, but as soon as it's released, it'll blow up like a balloon, fall apart on it. So know that the seals do come apart inside the systems while the engine is operating. We also might use fuel to cool things. We might use it for muscle to operate bleed valves, for stator vanes. I'll talk about stator vanes next week, I think. So we can use fuel as a hydraulic fluid. Works really well. We've already got it on the engine. We can also use it to heat the fuel. You can use it to lubricate accessories, drives, like in the gearbox and generators. So fuel is kind of a handy thing to have inside, just as an accessory on the engine itself. So the filtration. Filtration, the smallest is down to about 5 microns. What's a micron?
2 microns of filter.
Okay, so a micron is a millionth of a meter. Millionth of a meter. Pretty darn small. You can't even see 5 microns. You can't see light through 5 microns. Now the fuel system, as it comes out of the fuel control, it might use a dump valve. Now what we do is we use this dump valve, not all engines use this, but it depends on how long the lines are. We use a dump valve to stop the fuel going to the nozzles. Well, the engine will continue to run as long as you have fuel running through the nozzle, right? Yeah, so what we do is we use a dump valve to divert that fuel away from the nozzle back into the fuel system so it just runs in a circle then. We can also drain the manifolds that go to all the nozzles, so that once you pull the fuel, you shut the fuel off, the fuel is shut off, the engine ceases to operate. So we can use these dump valves. So rail fuel. Rail fuel refers to the fuel that is in the manifolds that feed the fuel nozzles. You may have 10, 15, 20 fuel nozzles on an engine, but there's a common line that runs between all of them to supply all of them with fuel, so the same amount of fuel, and they call those rails. Fuel pumps. You're going to have fuel pumps in the system, and probably strainers with those, because you don't want the junk and debris that's in the tank going through the fuel pumps. So you're going to have one in the fuel tank, usually to boost the fuel out of the tank. You'll have engine-driven pumps. Now these are delivery pumps. But then you're going to have mechanical and fuel control pumps. So as the throttle goes forward, what we're doing is we're taking this fuel that's supplied to the engine and the fuel control, and we're going to step up the flow incrementally through the fuel control and the FADEC. That's how we increase it. It used to be everything, like I say, was push-pull controls or connecting rods. Now it's all electric. So valves are going to begin to open in sequence 1, 2, 3, 4, 5. As the more valves open, the more fuel flows through the fuel control. Pressure bumps up, the volume bumps up at the same time. So the systems typically are stainless steel tubing. There's very little flex hose on turbine engines. Maybe the fuel into the fuel control, but most everything else is rigid plumbing, stainless steel lines that's silver soldered together, or it may have joints with packings and O-rings. Not too much flexible plumbing on the fuel control on turbine engines. So how much fuel does a big turbine engine pump? Well, I can tell you this. I disconnected a fuel control on a 787, and I had a bucket. Actually, I had two buckets, two Homer buckets. It filled from the wing to where the engine hangs. It filled 1.5 buckets of fuel just in that line that comes off the wing. That line is that big around. It's about 3.5 inches in diameter. So you know you're flowing some fuel. The takeoff power is one of those engines. Plus the pressure in that line is about 100 and some odd, 120 some odd PSI. Yeah.
Talking about a 5-gallon bucket?
5-gallon Homer buckets. Yep. Yeah. 1.5 Homer buckets. That's what came out of that line off the wing to the fuel control on the engine. So we're talking major fuel here on these big engines. Okay, so the basic layout, get a picture of this if you want, but this is the way that the fuel flows through the system. It's going to go from a tank. Usually we keep a little bit of air pressure in the tank. There's going to be a boost pump in the tank or a lift pump, and a low pressure filter, usually one right next to the other. There'll be a main shutoff valve in the wing or the nacelle. That will head straight to the engine-driven pump. Usually directly adjacent to the engine-driven pump, there's a main filter, and a pressure regulator. From there, it can split and go a couple of different directions, but usually there's a cooler or a heater involved. So we take hot oil, we can warm the fuel, or we can cool the oil using cool fuel. There's going to be a control or manifolds that run out to the nozzles. You're going to have manifolds to come directly. Two different ways this can happen is one, it can come directly from the fuel control, or it can go to a flow divider. So we pump the fuel out of the fuel control, heads down the manifold, goes to a flow divider. And what that flow divider does, it spreads the flow of fuel out to equally to every one of the nozzles, so there'll be a line go out to each and every nozzle. Instead of being manifolded together, each nozzle will have its own line, its own distinct feed of fuel, so they're all the same. And then it goes out to the injectors or the nozzles. And when you shut the engine down, it goes back into a return line, through a dump valve, back into the system, and then it can be recirculated back into the tanks. Once you take the fuel away from an engine, it's done. It doesn't run anymore. So that's kind of a step-by-step pathway for the fuel system off of the aircraft. So the FADEC system. Okay, so it's going to be controlling and monitoring a lot of different things. The FADEC is also going to have control of the reversing on the engines. Certain, maybe you've had fire protection, digital logic, haven't you? Okay, so you know about gates, right? Okay, so these things called gates, and certain things have to happen either physically or electronically, have to happen for something else to happen. So there's a sequence of events that are set up, and it has to move through from one gate to the next gate to the next gate. And so what happens here is, in the case of thrust reversing, the engine, as you might suspect, is set up to where it has to have the weight on the wheels for the thrust reverser to deploy. Does that make sense?
Mm-hmm.
Yeah. So, and the reason for that is because the aircraft, if you try to reverse an engine in flight, what it does is the airplane tries to swap ends, and you don't want that to happen, right? Well, they've had this happen before. for. FedEx were part of the problem. They initially came out on a 757. I don't know if any of you ever followed Formula One racing. There was a guy named Nicky Lauda. And Nicky Lauda bought himself, he got pretty badly burned, and he got out of the race car business, bought himself an airline, and he was operating in South America. This airline, Lauda Air, had one thrust reverser deployed, and the other one stayed, as they were cruising along about 35,000 feet over a jungle somewhere. One deployed, the other one did not. Asymmetrical thrust, the engine flipped around, broke up in flight, crashed into the jungle. What they found out was that, like anything computer, it had a bug in it. So it's all computer driven, had a bug in it. An anomaly occurred, and they never did figure out where it came from. But now, most aircraft carry dual channel FedEx. And so if some function occurs, if some gate, you slip through one gate to the next gate to the next gate, both FedEx have to agree before the event will occur. That is to say, if you want to deploy a thrust reverser, that airplane has to be on the ground. There has to be some other conditions met as well. So FedEx now talk to each other. They talk from wing to wing, engine to engine. They talk aircraft to engine, and so forth. So these things, they all have to be in an agreement before anything will happen. Okay. Okay, so they operate with three basic units. They have input sensors, controllers, and output actuators. Three basic units: input sensors, controllers, and output actuators. Now the controllers are all in the FedEx. The output actuators may be part of the FedEx, but they may also be things like bleed valves. They may be air valves that open and close, doors that shutter for oil coolers, any of that sort of thing. But all this relies on the input of various sensors set around the aircraft. Okay, so the early was hydromechanical, then we went to electrical systems, incorporated those, and now the current model is fully digital. Now they can be called a number of different things. So FedEx, use the word FedEx, everybody's going to know pretty much what you're talking about. But there are other names for it. It could be called an EEC, and this to your glossary, electronic engine control. MEC, main engine control. Or PMC, power management control. There's a couple of others I don't even remember anymore, but know that the FedEx is the thing that drives all of this stuff. Now again, the FedEx, there's really nothing for you to fool around with on a FedEx. They're sealed, and you're not supposed to be sticking your screwdrivers in those either. There are some connections to be made on them. There's plumbing and electrical to be connected to these FedEx. But there's really nothing else to do to them. When they don't work, what happens is there's a code comes up on the flight station. The code says, I'm not working.
What was
And then it's time to change it.
what was the M stand for in the P?
So which one?
PMC.
Power management control. Okay, so the inputs. Now, there are gonna be various stage temperature and pressure inputs, so different stages of the compressor, different stages of the turbine. There's also gonna be throttle position. Used to be the throttle was connected to a cable, the cable went back to the fuel control, moved everything was mechanical. Now, they put a spring and a friction device on the throttle just so the pilot feels like he has some control of something. The pilot is only operating a rheostat. Okay? Pilot is only operating a rheostat. That is to say, he is varying the electrical current back to something that picks up that current, a little motor, step motor, or some other device. Okay? So we call that now, instead of how much throttle you have in, 100%, whatever, we call it TLA, throttle lever angle. TLA, throttle lever angle. We're also going to measure the fuel flow in the ambient conditions, temperatures, pressures, and so forth. All these sensors. So there's going to be several bundles on a big engine. There's going to be several bundles of wire as big as your wrist that will feed inputs and outputs into the FADEC. So that's the inputs. And of course, everything is an acronym, or it has a contraction to it. So I think I have a few of these here. I'll show you what they are. Okay, outputs are going to include the fuel flow. It's going to be engine monitoring data and faults. Ignition, starting. It's all going to be part of the auto start system. And then any accessory controls. So how fast do we want the constant speed drive to operate? That is to say, the generator. How fast do we want that to run to keep the voltage up for the bus on the aircraft? How fast do we want the like that, the PMA to run? How much voltage do we want out of the PMA? So the PMA is a permanent magnet alternator. PMA, write that down if you haven't already. Permanent magnet alternator. Requires no input, it only puts out voltage. Should the FADEC or the ship's power fail, the PMA powers the FADEC to keep the engine running. Now, this little PMA only puts out about 15 or 20 amps, but that's all that's necessary to keep the engine running.
So it's like a standby power source.
Standby power source, yes, exactly. So you had, what was it, Singapore 370? Thing disappeared into the mists.
Mm-hmm.
You still haven't found it. PMAs were operating the engines apparently because the engines kept running. Somebody shut the power off or the power went off, but the engines kept running. So the PMAs is what kept the engines running on the aircraft.
Those put out enough power to keep pumps running? Fuel
What's
pump?
that?
They put out enough power to keep fuel pump?
Yeah, they'll run enough power to keep the fuel pumps operating.
Is that
So you got one on every engine. In that case, were there two engines on that engine? Two big engines?
so just fuel pump pumping is what important is on this.
Yeah, as long as you keep fuel going to it, it's going to continue to run. Yeah. Okay. So, as a general rule, these things are scheduled. You can write that word down too. These engines are scheduled by the manufacturer, and that is to provide the correct amount of fuel for any given throttle setting, engine speed, and pressure ratio. So a lot of input sensors to make all this work, but you have to have those inputs to make it all come together. So it's nothing the pilot, nothing the mechanics can do. There is one little thing that the mechanic can do. I used to make quite a bit of money off of this. In fact, I did little jobs for Pratt & Whitney on a contract basis. And when you go to the FADEC, there's a little chip that's attached to the FADEC. It's actually embedded in a cannon plug or receptacle. It's screwed on. It's got a lead seal on it. It's safety wired in place. What that will do is it will change all these parameters. That chip is a way of adjusting the thrust rating on the engines. So if you have an aircraft that does nothing but flies around carrying cargo, cargo is a big, heavy object, and so you need a lot of thrust to move it. But when you have passengers on board, packs, when you have packs on board, but you don't need as much thrust. So you don't want to burn as much fuel at that 100% throttle lever angle. So you reduce the thrust rating on the FADEC. You put this plug on there. Has to be a logbook entry made. You flip the data plate over to indicate the new thrust rating, and you're good to go. So they put chairs inside the airplane, fly people one direction, they'll fly cargo back the other direction. People one direction, cargo back the other direction. Pretty simple little procedure. Takes like 20 minutes to do it, and you can change the thrust rating. In the case of the engines I was working on, from 68,000 pounds, you can push them all the way to 78,000 pounds in about 20 minutes. Pretty easy, but what you're doing is you're changing the basic setting of the FADEC. Did a bunch of those for Delta compies. Okay, too much fuel for a given EPR or RPM, and the engine's going to stall. Too little fuel, and the engine's going to decelerate. It's just that simple. So you all know that now. So you all know fuel is everything to the speed of the engine. If you get too much, you can burn it up. Okay, so the FADEC is going to control all aspects of fuel scheduling and engine pressure ratio. Is there one more there? Nope. So we'll start with these. So it's going to sense the EPR, the engine pressure ratio, the PLA, which is also the TLA, power lever angle. Might add that to your glossary. It's going to sense the N1 speed. That's going to be your low pressure compressor and turbine. So it's going to be looking to see what the engine is doing speed-wise. P2, T2. So this is pressure 2 and temperature 2. This is going to be a little thing that looks like a pitot tube in the inlet. But what it's measuring is the density of the air that comes into the inlet. So you go to Phoenix on a hot day, a lot of times the airplanes can't even take off because the air is too thin. The scales on the performance charts don't even go to some of the temperatures that you get at a hot afternoon in the summer in Phoenix. So the airplanes have to wait until the temperatures come back down into the scale, the performance scales for the aircraft engine. All right, so it's measuring the pressure and it's measuring the temperature at the inlet of the engine. What's going in the engine air-wise? Temperature and pressure. T12. T12 is a pickoff point way at the back of the engine. It's a turbine. What is the temperature of that turbine, the exhaust gas at the turbine at the T12 position? So this is going to be one of the last stages of the turbine. So that's going to, when you combine all these things together, that's going to have an effect on how much fuel the FADEC is going to meter to the engine. So let's go back to Phoenix. It's pretty hot, but you're within the performance parameters of the engine. What's going to happen? So the temperature is going to be pretty high. What's the air density going to be? Pretty low, right? So the aircraft is going to think it's already at 10,000 feet because of the density altitude, even though it's sitting at the elevation in Phoenix. So would we give it the same amount of fuel as if it was sitting here in San Diego at sea level?
No.
No. And so what's that going to do to the performance of that engine? Because we're going to give it less fuel. It's going to make less power. Now the airplane will fly, kind of stagger out of there. But what the pilot has to know is how much weight can I put on board the aircraft. You can't put as much weight on board the aircraft. Somebody's going to have to step off. They're going to get those tickets for the next flight tomorrow or something. They're going to stay in the hotel. But the airplane can't go with too much weight and not enough thrust. There's another one called PS12. And this is also known as burner pressure. How much heat is the engine making? And that translates into pressure at the burner. It's also going to pick up N2 speed. How is the N2 running compared to the N1? So if you've got very thin air, chances are N2 is going to be running somewhat slower than N1. And then you've got the EGT, or the exhaust gas temperature. And that's directly related to what comes out the back of the engine. So you can see some engines have another 10 or 12 different pickup points, but these are pretty basic pickup points on the engine for determining thrust and the amount of fuel that should be introduced to the engine. Okay, so we're going to move on down the road here just a little bit. I gotta skip some stuff. I have some stuff under construction here, but it's not ready yet. 532, 556. Okay, so you kind of get a sense of how the FADEC systems work. So it's taken a lot of input information. It's computing it all together, and that's nothing more than the FADEC is. It's just a computer you don't have a screen on, and it's taking all this information, munching it together, and it's telling the engine what to do based on what it sees. Okay? So it's going to give you fuel outputs, it's going to give you temperature outputs, things you're looking for. The oil temperature starts getting too high, it's going to open a door to allow an oil cooler to operate. It may turn on extra oil scavenging pumps. It may do all sorts of different things. It's all part of the general health of the engine. So the FADEC controls everything. It's like a modern car anymore. There just isn't anything that you have to really tune up or fool around with. So you do a fuel change, fuel control, or a FADEC change on an engine. Do you have to do a trim check on it? No. No. What do you have to do?
Pressure check.
Leak check. Make sure everything functional check. Make sure everything works properly. Yeah. I can tell you that I've done 100 of those things, and you end up changing them. Pretty soon you got to hang around for somebody to run the engine because they want the customer to run the engine, right? So you got to hang around 3-4 hours. Finally one day I said, screw it. I never had a leak. Guess what happened? My head hit the pillow and it was a leak time. Get back up, get your ass out there, get that thing fixed, right? So know that always functional check this stuff or leave somebody behind who can handle it before you go back crawling to bed somewhere. All right, so it's 30 after. Why don't you come back a quarter till and we'll talk about fuel nozzles real quick, and that'll be it for tonight.